Okay, so welcome everyone. And in this session, we are going to see the importance of materials which are powering the electronics world, right? And we have already talked about in one of the slide that this is the brain or the power, which is power in the sense the brain inside all of these different applications which we see. And you can already see the impact of this tiny chip which is inside these systems, which brings intelligence into the system, right? Otherwise these are just mechanical system. The intelligence is brought by this chip, which is what we all are trying to make better and better every day, right? So if we see this also, I have talked about in another video where what is the supply chain, right, to get a product finally, what different stages it can go through, and what are the real key members. Let's say these are not very exhaustive list of companies, but what are the companies and where they are working on, right, which part they are working on. So if you see typically Foxconn we were talking about, they are working on mostly assembly. Either it is a board assembly, which is the motherboard, because the series name which we said is like semiconductors from atoms to motherboards, right? So we are going to talk about everything in that scale. So now if you see that you are going to build a final product, all of this, the main thing which is common across all of this except the design, you would need materials, right? So you see either in the when you are doing wafer fabrication, you need silicon wafers, and silicon wafer is not the only material which is going. There are other materials which we are going to see in this series also, in this particular video, that what different materials are there to manufacture a chip itself, right? Then we really need a lot of materials again in the packaging, because and this could be very different materials than what was used to make a chip or a wafer fabrication, right? Similarly, when we go to board assembly, where you are putting these packages on a motherboard, you may need very different materials again, right? But what is very, very common across all the pipeline or the supply chain is that you do need materials to make these systems, right? So that is the common thing. So now, first we start with what we were talking about already, that the AI which we are seeing, which is when you have a query and you are putting that query into your chat GPT, it is going somewhere in the world, which is what we say cloud, which is not that cloud. So that's mean it's a server somewhere or data center sitting somewhere remote location in the world. It can be at the ocean also, right? So it can be at the depth of the ocean, it can be at a mountain. So that does not mean, but the computing is done by this system, which is what we see as of now, where Nvidia, when they give their AI system, this is the kind of way they are arranging their system. And this is coming, this is a technology platform. I forgot to add the reference, but this is, you can look at, this is from TSMC, and the technology platform is known as CoWoS. What is the name is CoWoS. The meaning is you are putting a chip which is put on a wafer, and that you are putting on a substrate. So you see chip on wafer on substrate, right? And that is what the meaning of CoWoS in this beautiful architecture, which is powering all the AI system as of now, right? All the data centers, AI data centers, is this bad boy, or let's say good boy, right? But there are problems with this, and that we will look at. But let's first look at this, the importance of materials, right? So where are the materials in this? Because we see just the boxes. So if we see die, which we are going to talk about in a short while, what is there in the die? But this die, now it is, think of this like you have houses in a city. These houses need to be connected by the roads, right? Because these houses need to talk to each other. So that means when you are asking a query to say, oh, who am I, in your AI chat engine, it goes to this system, right? Obviously, it's broken down into information which these systems understand, which is your digital format. Then it goes into this, let's say, goes to the logic and saying, okay, that guy is asking, who am I? What is the answer for that? So that means it's going to break those into the operations which this guy knows, which this die or this logic knows. right? Which we have talked about in another video, that what is inside a microprocessor, right? Or what is inside a die. But now if we understand that this logic die is going to apply some operations and going to answer that question, when it is doing so, we discussed the importance of the memory also in the last one of the video, where we were talking about microprocessor, why memory is needed. And we give an analogy that it is like a brain, right? When somebody is asking me question and giving me information, before I can give my question to him, I wait. So that means in the meantime, that question is stored in a memory, because I have to store it somewhere. That question may come on a 13th slide of this PPT, right? But I have to store probably, because I can ask in the end. This is the same way you see here the HBM, which is doing the throttling of this data to the die, because die is only able to think. It does have some memory, but it is very less. So the main memory is what which you require a lot of this memory for your AI systems, because you are having very big LLM models which need to store all these weights and everything, which we will talk in some other video, what is there inside. But as of now, we focus on materials. So the point is that in HBM, you see that there is this connection, or the between these two are needed. So that means to make the connection, these wires have to go. Now, you could say, okay, why do I need bottom wires? Why these cannot connect like this, right? Just on the side. So the point is, when you are putting that, you do need a substrate, right? So you cannot put this logic die into air. So that means there is always what you are starting with is a board, right? So this things, what you see gray thing, which are typically called bump. That means these are bumps, means solder bumps, which are connecting. So this you would have heard even in, if you have probably faced this issue in your mobile, that your bumps or the soldering is not correct, right, to the board. And the reason why soldering is not correct, because these things which you are connecting, which are nothing, it's some mixture of, let's say, the copper, tin, silver. So some materials which are coming in some alloy and making this possible to connect this to your board, right? So that means they are the ones who are making this information pass to the substrate from the board, right? That is what you can think of these as big bridges which are passing this information. Now, suppose when you drop your mobile, right? And you drop your mobile, what happens? During that drop, it is going to experience a big shock, right? Because suddenly the gravity shock, because the mobile has dropped. Now, when your system, which is inside that mobile, similar to this, you will see that what could happen is this solder can break, right? When this solder breaks, means that now it would not work anymore. And that is the reason why you see in your mobile that your OS is not working, right? And then the person tells you, when you take you to the technician, he says, oh yeah, I have to do the soldering again. That means I have to remove this chip from the board, and then I have to do the solder again. That is nothing. It's basically he's putting this array or the solder attach, which is a material, obviously, as I said, which is, let's say, which we know in the industry as something called SEC alloy, right? So SEC means tin, silver, copper. So these are the three materials by which you make this material, which is SEC, and then you are attaching that to the substrate. Now the question is, what is a substrate? And I think if you have seen a board, typically this board which you have seen in the PCBs or so, this board is a laminate board, right? So it's a plastic board, which is what we know as the printed circuit board also earlier. But here it's a laminate is a substrate. So it's an organic substrate. Okay. And now this organic substrate, obviously it has to connect these wires, whatever were there on the board, has to connect through the substrate to this. So that means there are some material again needed through the substrate. Obviously that would be something wires which would be passing through this substrate, which are through vias, right? Because we have to put them through this substrate. Now, once we come to the level of, let's say now we are going to, because now one approach is I could put the directly logic die on this substrate. But what I lose in doing that is it's again like how I connect different houses. So if the number of houses are small, probably I need smaller or lesser number of roads. But if my houses become too much, then I have to plan it out. right? I may need to put in between junctions. I need to put in between some other roads, secondary road. There is a lot of planning which you have to do. Basically, that is what the whole purpose of this layer, which we call as wafer or interposer, is put here, which is the gray portion which you see in this plot, right? So this plot is actually, or this thing, gray portion is your interposer. And now this has to provide these connections, internal connections between this logic and memory die. Okay, so this logic has to talk to memory not through the substrate, but through this interposer, which is typically made of silicon. Typically, obviously, there are issues with that, and that's why TSMC has been actively working on replacing this interposer with some other materials. But as of now, most of the chips were in the last generation, at least till Blackwell, they were on interposer of silicon. And then you see that they are connecting these wires which are coming from the logic and memory, right? So now what is these wires? Obviously here there is only one gold standard, and which is copper, right? So we are going to follow, if there is a wiring, which we are following from all the way from the die, which I will go briefly into in the next slide. But here you see these are copper wires, right? So copper wires passing through your silicon substrate, copper wires passing through like this connections. So the yellow is the copper wires, and these copper wires, when they are passing through the silicon, they are something through which we call as TSVs, or through silicon vias, right? Which is what connects. And what are these orange and the gray portion, dark gray? They are basically, again, these are called micro bumps, because they are not as big as these soldiers, the bottommost soldiers, but they are smaller in size, and that's why they look the way they look, right? And this you can see from the picture, which is directly a TM cross section, or from die, where you see these big things, which are your, let's say, bumps, while you see the smaller ones, right, which are your micro bumps, which you are connecting. Okay, so that's how you see and material choice could be very different. So here I am using SEC material. Here for micro bumps, I could use just copper pillars, and with some finishing materials like titanium, right? So the choice of material now depends on at what abstraction level and what is the purpose of that particular contact or material. So basically it's like, if from the house, if I'm going, I may need a very small road, and that road could be maybe made of concrete, it could be made of, let's say, just the dust, right, or the sand. So that depends on what do you require from that road, right? What we need from here, when the logic is talking to memory, we need a very good bandwidth. That means we cannot bear latency. We cannot bear speed is of paramount importance when the logic is talking to this. So that's why the copper has been one of the workforce in the die, inside the die, how different transistors talk to each other. So that's why this is always based on what we have learned in the last 20-30 years from copper. We apply the same learnings to this, connecting this. Now, what is the logic is connected to these wires? It could be also copper to copper connection, or it could be pillar to pillar, but that is also copper. So it's typically copper to copper connection, but the way we connect them can differ in technology, but the material still remains copper here. Okay, so that is what you see, the importance of the interconnection. And that, if you read any article, typically for semiconductors, you see interconnections are becoming the bottleneck. So people, when you hear this, which is what we were talking in the last discussion also, something called memory wall. And people say that logic and memory independently, they are working very fast, very, very good. But the problem is the connection between the two, because that is bringing the latency in the system. So when I ask a query, this guy is doing the operation, it takes a lot of time to bring that data back and forth from the memory. That is what the real bottleneck in the current system is. And that's why if you are working on some interconnect technologies, probably very, very interesting area to look at, right? How to enable a very good interconnect, right? So now we go to the brain of this all, which is your die, where we will just look at inside the material. So this on the left, you see kind of a typical logic die, right? Where you go all the way. So where is silicon? So you know the silicon is obviously sitting on the bottom, right? Because you are making everything on a substrate. And when we make a die or a chip, the substrate is typically silicon, right? That's what the workhorse of the industry for last 50, 60 years, and that is continuing to be the workhorse. So that means on silicon wafer, then I make transistors, which could be made of a silicon channel or could be made of different channels, right? People have been trying very different channels, which we'll talk about in some other video. What are in the logic transistor different channels people are talking about. But here you see silicon, on top of silicon, we see this transistors. Now in the transistor itself, there are multiple materials which are going, right? So if we say transistor, which is the typical is MOS, right? MOS FET. So that means already in the name itself, you see three different materials. What are those? Metal, which is your, let's say in this is the pink portion, which you see, right? This is the metal. Then you see O. O, maybe it will be very small here, but you can think of O as this yellow thing also is O, oxide. No, not the gate oxide, but it's the oxide. You see the gray, the red, dark blue is also oxide here, which is used for spacer, right? So there are different O which you are using, oxides. Then there is semiconductor, which is our silicon, right? So you see already three materials which we study widely, or we divide all the materials in saying this is metal, this is dielectric, or let's say insulator, and this is my semiconductor. So all three are used just in this portion itself at the first layer, right? Now, after we move through the first layer, you see how do I connect them? So it's the same question. I have billions of transistors. I have billions of houses made on the silicon wafer. But how do I connect them? And now the question is, if you do just one flyover, let's say you could say, okay, I could connect just by a road, right? But the question is then, if you do by the road, would you be able to manage the congestion which you are going to have? Because it's a similar problem that I'm going to connect billions of houses. I'm going to face congestion, right? So that is why you see that typically what is made is flyovers, right? So flyovers are a way for you to reach rather than going through this transistor. So let's say a transistor here wants to connect to a transistor which is very far. So why do I go through the first layer? I can go all the way to the top and then go back to that transistor, right? So that is why these metal layers are typically made. And the whole purpose of these metal layers is to connect these transistors to each other reliably, right? And there the materials which we see are largely, again, as you can guess, the orange portion is the workhorse of the semiconductor industry for last 20 years. This is your copper. Before that, it was aluminum. But now it is copper, and we see the copper has to also, these two lines, they don't need to talk to each other because this is a separate transistor, this is a separate transistor. So in between you put something which looks like a concrete, but it is not, it is a dielectric. So it's another dielectric way. That means now you have a metal separation using dielectric because it's a non-conductive medium in between. And then you see that you are putting dielectric metal, dielectric metal, dielectric metal on top of each other to reach the end of the chip, right? And as of now, we see we typically have in the dies which are made with the recent nodes around 10 to 12 or 13 even. And it has been increasing from the time I started my career. So I saw maybe 7, 8 or 4, 5 we were starting with, and then 7, 8, then it started increasing again 10, 12, 13, 14. So it is increasing. And the reason is very simple, because if you can increase the number of transistor on your chip, similarly, you increase the number of houses in a city, you have to make more flyover. That is what it is doing the industry. And that is what is also very, very challenging problem sometimes to make the reliability concerns of these on these wires, right? So that is what typically you see inside the die of the logic. But on the right, it's a very simple way of looking at. Again, you see this is a memory die, which is your HBM, where if you know the technology, it's made of DRAM. DRAM is nothing. It's a transistor with a capacitor. We don't need to go into it. We'll go into it in some other video. But in this, the idea is that IC, word line, bit line, all these things which you see gray are your what are these? So this could be your metal on the side, right? So the metal filling which you will have, obviously, this is all metal gray, and you will see somewhere that these black portion are your dielectric, right? Which is separating these two. So that is how you would see that so many materials which are making these system, what we just saw, possible. And these all materials have to understand each other, understand its role, what my role is, right? And we have to also understand the limitation of that material when we are putting that there, right? So with that, I would end or stop this thing, and we will see next time on another video, right?